Hello everyone, my name is Shuangfeng and I'm coming from University of California, Merced. Today I'm going to present our work on fast charging of batteries using Cascade-Control-Barrier functions. The agenda of my presentation today has 4 parts. Firstly, I will discuss the motivation behind our work. Next, moving on to the theory, I will present the overview of the system, then introduce the model of the battery. I will give a brief introduction on the control-barrier function theory and how we applied the cascade control-barrier function to battery fast charging scenario. Next, we will share the most exciting part of our presentation, the experimental results and analysis. Finally, I will show the conclusion and give a summary and outlook for this project. Li-ion batteries are widely used in electrical vehicles, smartphones, and other portable applications. High battery charging rates are usually desired to shorten the overall charging time. For example, no one wants to wait at a charging station for hours during a holiday travel. On the other hand, battery charging without the proper control could be dangerous. Overcharging, overheating may result in battery fires and explosions. So it still remains a challenge on how do we balance these two objectives and maintain the fast charging rate and guarantee the safety at the same time. In this project, we propose a cascade control barrier function that divides the battery fast charging and safety design problem into a multiple layer problem. Here is the overview of the system. Starting with the battery, we have model identifications for identify a battery model. Using the battery model, we use a state estimator such as extended gamma filter to estimate unmeasurable states. We also have an unconstrained charging protocol that's generating a reference charging current that's feeding into the battery. However, at this stage, there's no safety concerns taken into account. To addressing the safety, we use a cascade control barrier function controller as a safety layer. So the cascade control barrier function controller generates the control action under the evaluation of state of charge, temperature, and terminal voltage. If any of the states is reaching the safety limits, the CBF going to reduce the actual control action that's feeding into the battery. Overall, the system have an outer loop that's addressing the fast charging and the inner loop that's going to addressing the safety concerns during the charging problem. Here is the model of the battery. So we first started with the electrical model where the battery is modeled as the open source voltage VOC in series with the inner resistance R0 and the 2 RC pairs. This model can be summarized into a 3-stage system. So the first stage is the state of charge. The second and the third stage is the voltage crossing the RC pairs in the equivalent circuit. Next, we have a thermal model for the battery, which we're modeling a battery as a cylinder, and the center of the battery is generating heat. And there are conductive heat transfer between the battery center and the battery surface, as well as the convective heat transfer between the surface and the ambient temperature TF. So this system can also be modeled as 2 states. The first state is the center temperature of the battery, and the second state is the surface temperature of the battery. Overall, this concludes the battery model with 5 states. To use control barrier function in first safety, we start with translate the voltage, state of charge, and temperature safety requirements into a set of safety states. As shown in this figure, the states inside the green box are within the safety limits. Those states can be represented by a safe function where C is greater and equal to 0. We use the control barrier function to formulate forward invariant conditions for control affine system that guarantee the system states stay within the safety sets. Such guarantee can be represented by a linear inequality constraint with respect to the control input U. The linear inequality constraint from the control barrier function can be integrated into a quadratic programming controller and combined with other outer loop controllers by minimizing the difference between an unconstrained control action and the optimized safety constraint action. Because the problem formulation shows that the cost function is quadratic and the inequality constraint is linear, this problem is convex and can be solved easily with a simple solver. To addressing the safety of the battery during fast charging, we first trying to integrating all the safety limits into one CBF-based controller, and we call this controller as the central CBF controller. In this problem, we're trying to minimizing the difference from the reference current and the actual optimized current fitting into the battery. And the control action U is subject to the terminal voltage, state of charge, temperature, and input constraints. Now looking closer at the temperature constraint, we would notice that the control action U is entering quadratically into this problem. This is raising an issue because the nonlinearity in this inequality constraint makes this optimization problem hard to solve. To reduce the computational burden of the central control barrier function, we decouples and decompose the battery model into an electrical model and a thermal model. And we split up the original central CBF controller into two cascaded CBF-based controllers. The first controller is only dealing with the state of charge and the terminal voltage constraint, and the second controller is only tackling the temperature constraint. By such reformulation, we're splitting up the original central CBF problem into two convex quadratic programming optimization problems. The first problem is very similar to the original central CBF optimization problem, but without the nonlinear inequality constraint coming from the temperature. The temperature constraint enters to the second optimization problem through a variable change. By changing the U square into a variable W, we're able to converting the nonlinear optimization problem into a linear optimization problem with linear inequality constraint. So the linear inequality constraint helps to ease the computational burden because it's convex and easier to be solved. We did a simulation to compare the computational cost for central control barrier function and the Cascade-Control-Barrier function. In the simulation, we simulate the battery charging from 0 to 1,500 seconds. On the left, the plot is showing both central CBF and Cascade CBF are able to prevent the battery reaching an unsafe region, which is marked as the red line in the plot. However, with regard to the computational time, the figures on the right show the computational time of the Cascade CBF is much faster comparing to the central CBF. On average, the Cascade CBF is 4.3 times faster than the central CBF. At last, we started the experimental validations to validate the performance of a Cascade-Control-Barrier function. The test setup consists of a power supply, a battery, and a sensor board that's measuring the temperature, current, and the voltage applied to the battery. We also used the DSpace micro lab box controller to integrating the control algorithms and processing the measured sensing data. The charging protocol is sending from the macro lab box to the power supply using an Ethernet connection. Here is the fast charging experimental result. In this experiment, we compare the Cascade CBF with the traditional constant current, constant voltage charging algorithm. Without the safety constraint violation, Cascade CBF is 20% faster than the constant current, constant voltage charging. Looking closer, we can see the battery charged under Cascade CBF have 4 stages. At the first stage, the Cascade CBF charged the battery with the reference current 15 amp. At stage 2, the terminal voltage constraint is active and the charging current is reduced. The next stage, as the charging goes on, the temperature rises up and the temperature constraint is active, so the charging current is further reduced and stabilized around 6 amp. Near the end of the charging process, the state of charge constraint dominates, which further reduces the charging current to 0 amps and concludes the charging. At the end of this section, I would like to also mention that the proposed control barrier function-based algorithm can also be applied to discharging scenario. We did a preliminary test to demonstrate that. We used a programmable electronic load to request the discharging current from the battery. The request current is following a discharging current profile from a driving cycle. And as shown in the plot, the Cascade CBF ensures the safety during the discharging phase, just like the fast charging test. In conclusion, our work presents a Cascade-Control-Barrier function-based battery fast charging algorithm. The proposed algorithm is 20% faster than the traditional constant current, constant voltage charging. It is also able to enforce terminal voltage, state of charge, and temperature constraints. The proposed algorithm is also computational efficient because it only requires the solution of 2 low-dimensional quadratic optimization problems. In the future, we will combining the batteries charging and discharging together in one driving cycle to demonstrate the use of control barrier function on both scenarios. And we will extend the control barrier function to battery pack tests. In addition, we are adding more safety constraints in the formulation of the CBF, including battery aging and battery degradation considerations. This concludes my presentation. Thank you.